Hey guys, I have got 10 minutes to present to you the Marslink constellation. So I have a small company called Dynamic Orbits. My name is Julien. Matthew was here in lab this morning. And what we do at Dynamic Orbits is to model and design satellite constellations and ground network. Just basically place the satellites in orbit and tell our customers where to place them. And I was just going to go through real quick because we only have 10 minutes. Oh yeah, that was my wedding 2 weeks ago. This was the Mars themed wedding. So you have the rockets here. Next is the cake. We have a champagne bottle that with the Mars label. I'll go super quick. This is when I'm doing some marshmallows, flaming. That's marshmallow. We had an ad for the wedding, and that's the cocktail bar, the green hab. So, anyways, this suite came out 1 year ago, where NASA said we need 4 megabits per second link between Earth and Mars. So we have 3 companies here who responded, and SpaceX said we'll do 1 gigabit per second. And I was like, wait, how? So that's why I dropped everything I was doing and focused on this thing, just for fun. The problem, of course, is the inverse square law, meaning that you need a bunch of relays if you want to connect between Earth and Mars. If you don't have relays, then you're going to get 1 megabit per second. And you cannot have relays like they were shown on this slide, because orbital mechanics will move that around a lot. So you need a bunch of relays, basically, not just 4, like you can see on the right side here. So we need a heliocentric constellation that will reduce distance between the relays to have as many satellites as possible. And since you have many satellites, just like Starlink, use economies of scale to produce mass manufacture them at a lower cost. So these are 3 different design options, like high-level options. One here, like everybody's seen this, is like classic home transfer, where you have the Earth orbit here, the Mars orbit there, and the home transfer orbit here. So now, just please understand, this is not just orbit. It's a bunch of satellites here. There might be like 500 satellites on this ring, each passing information from one to the next at the speed of, say, 500 megabits per second or so. And what you see here, the little lines, is just lines. It's links between this satellite and that satellite that passing information. So when it's blue, it means the throughput is really low. So let's say you have 500 megabits per second or 20 or something like that. When it's red, it means it's very high because the satellites are very close to each other. They're so close you can see it. If you look at this one, it's more spread out. The density of satellite is less. You can actually see the gap between one satellite and the next. So actually the links, they're blue, meaning the throughput is very low. But here it's relatively higher. Okay, and the reason for this three design, this is really serial communications, essentially, the way it works. So that's Earth. The data flows like that and like that until it meets the next ring. And then the data flows on that ring until it meets the final ring. And then it flows the planet. So it's really serial communications. You have 2 pathways. One going this way, one going that way. Okay? And that's a hybrid with like a few more of these transfer orbits, but there's 3 of them here. And this is parallel data flow, where it still spreads out like that, but then there's 2 big rivers divided into smaller streams, and the sum of all the streams all around, even if they're low speed. So this was 500 megabits per second between one satellite and the next. This might be just 2 megabits per second, but you have 300 satellites doing this. So now you have if you have 500 satellites doing 2 megabits per second, then you get to 1 megabit per second. That's essentially if you unwrap this constellation we saw on the right side. You just make it flat. Well, that's just the big 2 rivers I was talking about, dividing into streams, and then the streams meet up again to form those 2 big rivers to get the 1 gigabit per second. So that's a video of the actual model. So you can go to marslink.io. That's our website, and the model is here. And it can accelerate time, look into the future. And then you have a few sliders here. And the sliders help you design the constellation you want. More rings, less rings. You can increase the number of satellites within each ring. So I mentioned you can have 2 megabits per second, 500 gigabit per second, depending on how far the satellites are from each other. You can get rid of the circular rings and put eccentric rings like here, and change the distance of the rings from the sun, the eccentricity. You can also do the special case of the classic command transfer type where you have only one ring. Here you have only the other 3 rings. So anyways, you can model anything you want and have fun and spend hours. But here I'm just comparing the different, the 3 high-level designs. And the classic movement, while it's cheaper, it is the worst in terms of the performance. The latency is really poor. The resilience to failure, if you have a satellite failure, then the data rate drops crazily. You don't have any launch opportunities. And if you have in-transit spacecraft, then they're always going to be in the wide area and very rarely near the links, so they will not be able to connect to the internet. But the circular rings, on the other hand, there's always a satellite near your spacecraft, so your spacecraft will always have internet access. It's great for launch opportunities. It's great for resilience to failure. So if you lose 2 megabits per second on one satellite, you still have the rest of all the other satellites contributing to the network. And the latency is always the best possible. So from here, we're going to look at circular rings only. One important detail is this whole thing depends on the laser technology, like how it can improve in the next couple of years versus the cost when you mass manufacture them. Our baseline is the Starlink laser link, which is 100 gigabit per second, 5,400 kilometers. And from here, we scale to calculate what is the throughput at a longer distance. But we think that a lot of things here listed could be improved to keep a low cost, but improve the capability. So TSAT is already operating 70 times better than the baseline Starlink. Psyche, the NASA mission, offers a lot more. But of course, this is so much more expensive. This is a custom thing. What we need is a mass manufactured laser that is cheap, but more performance. So here is the sensitivity analysis based on circular rings. And we have different laser technology improvement factors from the baseline. So 1x is what Starlink has today in terms of the inter-satellite links. But this is 64 times better than today. That's 1,000 times better. And so there's 2 more inputs to the sensitivity table. The in-rings megabit per second. This determines how many satellites you have inside a ring, how close they are to each other. And this is how many rings you have, concentric rings. And so in orange, I identify all of the solutions that give you 1 gigabit per second. So let's just focus on this one. We have almost 1 gigabit per second, and it's 1,700 satellites. And now we can just have a look at what it would be. This is what it would be. So this here is the Earth ring. This here is a Mars ring, and the other ones are intermediate circular rings. So when it is white, it means no data is flowing through at the moment. When it's red, there's a lot of data, the high throughput, and when it's low, it's a low throughput, so it's not being used a lot. So we can consider that the design is okay. You do get 1.2 gigabit per second. Of course, this varies based on the topology of the network, which changes all the time. And the cost here is 11.7 billion. The detail is here, and you can have more detail if you press this button. But yeah, just how it looks. And the latency, depending on the topology, so the alignment of the planets is between 6 minutes and let's say 1 hour. We have no time to go into the detail, so that's why I'm going pretty quick. That's the technical summary for each of the rings. So we know how many satellites, how many laser terminals per satellite, how many deployment flights, we assume Starship, of course, how many tanker flights to refuel the Starships. Those rings which are further out require more refills, refueling, because the Starship will need more fuel to place the satellites on the transfer orbit. And we calculate the fuel requirement as well. And then we transfer that to a financial summary. And that's where we see the $11.7 billion requirement for this specific configuration. Now in the same table as before, the sensitivity analysis, but I removed the number of satellites and added the number of $1 billion required. So we find again the 11.7 billion for this constellation we found. If your technology does not improve as much as 1000x, but only say 250x, then you're stuck with like more satellites, and now it's 28 billion, not 12 billion. But if your technology improves more, say 4,000 rather than 1,000 here, then you can get by with 5 or 6 billion. Of course, that's only the satellite cost, the launch cost, and the cost assumptions are there. So 20 million per starship, and for each tanker. Satellites 5 million, latest terminal 200K, 4 terminals per satellite. Of course, that can change. And if you go to the simulation on marslink.io, you can change those assumptions to get a different result. Yep. Thank you very much.